Welcome to this walkthrough of LeetCode problem number 972, equal rational numbers. In this problem, we'll explore how to determine if two strings representing rational numbers are mathematically equal. Get ready to break down the concepts and approaches step by step. Let's dive in. In this problem, we are tasked with determining if two rational numbers, represented as strings, are equal. The numbers can be given in three formats. First, as integers, which are non-negative numbers without any decimal point, like 5. Second, as non-repeating decimals, where there is a decimal point but no repeating sequence, such as 5.12. Lastly, as repeating decimals, which include a repeating sequence and their decimal part enclosed in parentheses, for example, 5, 3, or 5.1, 23. Two rational numbers are considered equal if they represent the same numerical value. This means that even if the numbers are expressed differently, they should evaluate to the same value. For example, one number might have a repeating decimal while the other does not, but they can still be equivalent. The input will consist of two strings, and our job is to return true if the numbers are equal, or false if they are not. Let's look at some examples to better understand the problem. In the first example, the inputs are s equals 0, 52, and t equals 0.525252. The string s equals 0, 52, represents the repeating decimal 0.525252, or 52 repeats indefinitely. Similarly, t equals 0.525252 has the same numerical value, even though it is written without parentheses. Since both numbers are equivalent, the output for this case is true. In the second example, we have s equals 0.16666 and t equals 0.16667. Here, s equals 0.16666 represents the repeating decimal 0.166666, where the digit 6 repeats indefinitely. On the other hand, t equals 0.16667 does not have a repeating pattern and rounds off after 5 decimal places. Because the numerical value of t is slightly larger than that of s, the two numbers are not equal, and the output is false. In the third example, the inputs are s equals 1.0 and t equals 1. The string s equals 1.0 is equivalent to the integer 1, and t equals 1 is also the integer 1. Since both represent the same value, the output here is true. Now let's consider the constraints of the problem. Both input strings, s and t, will have a length between 1 and 20. These strings may include digits, a decimal point, and parentheses. The integer part of the number, which is the portion before the decimal point, is guaranteed to be non-negative. It can also be empty, which should be interpreted as 0. If there is a repeating part in the decimal, it will always be enclosed in parentheses and will not be empty. For instance, 1, 0 is valid, but 1 is not. Additionally, if a repeating part exists, it will begin immediately after the non-repeating part of the decimal. Finally, the input strings are guaranteed to represent valid rational numbers, ensuring that we don't have to handle malformed inputs. To solve problem number 972, our goal is to determine whether two strings representing rational numbers are mathematically equal. The input strings can represent integers, terminating decimals, or repeating decimals, so we need an approach that handles each of these cases correctly. One approach we considered is the brute force method. Here, the idea is to convert both strings into a common format, such as floating point numbers or fractions, and then compare them directly. To do this, we would first parse the strings to identify the integer part, the fractional part, and any repeating sequences. Once the repeating decimals are expanded to a sufficiently large precision, we can compare the results. However, this approach faces some challenges. Floating point precision errors are common when working with repeating decimals, and expanding them to a fixed precision doesn't always guarantee mathematical equality. Additionally, the time complexity depends heavily on the precision chosen for expansion, making this method inefficient for long repeating sequences. While intuitive, this approach lacks the reliability and efficiency we need for this problem. Another approach we considered is the fraction conversion method. Here, the key idea is to represent each rational number as an exact fraction, such as a numerator and denominator, to avoid any precision issues. To implement this, we start by parsing the input strings to separate the integer, non-repeating, and repeating parts. Then, we convert the rational number into a fraction. For the non-repeating part, we use standard fraction representation. For the repeating part, we apply the formula for a geometric series to calculate the fractional equivalent. Once both numbers are represented as fractions, we simplify them to their lowest terms and compare. This method has significant advantages. It avoids floating point precision issues entirely and handles repeating decimals exactly, ensuring correctness. Additionally, the parsing and fraction operations are computationally efficient, making this approach optimal. Another idea we explored was direct decimal expansion and comparison. However, this method requires careful handling of repeating decimals and can involve unnecessary computation if numbers are equal early in the expansion. Like the brute force method, its efficiency depends on the expansion precision, making it less reliable. Ultimately, we selected the fraction conversion approach as the best solution because it excels in precision, mathematical rigor, and efficiency. One key observation that guided this decision is the realization that repeating decimals can be represented as fractions using the formula for a geometric series. For example, the repeating decimal 0.3 converts to the fraction 1/3 because the repeating part forms an infinite geometric series. This insight allows us to handle repeating decimals exactly and compare numbers in their simplest fractional forms. Additionally, this approach avoids the pitfalls of floating point arithmetic, such as rounding errors, and seamlessly handles edge cases like 0.999 being equal to 1. It is also computationally efficient, as the problem's constraints make parsing and fraction manipulation feasible within competitive programming limits. In contrast, other methods, like brute force or direct expansion, are more error-prone and less efficient. While the fraction conversion approach requires parsing and arithmetic operations, the trade-offs are justified by its guaranteed correctness and robustness. In conclusion, the fraction conversion approach strikes the perfect balance between correctness, efficiency, and robustness, making it the ideal choice for solving this problem. By avoiding precision issues and ensuring mathematical rigor, this method provides a reliable solution that handles all edge cases effectively. Its efficiency and accuracy make it well-suited for competitive programming scenarios, where precision and performance are critical. In this problem, we are tasked with comparing two strings that represent rational numbers to determine if they are mathematically equal. The challenge lies in the fact that these numbers can be represented in different formats: integers, terminating decimals, or repeating decimals. For example, the string 12.3456 includes an integer part, a fractional part, and a repeating part. To solve this, the first step is to parse the input strings. Parsing involves breaking each string into its components: the integer part, the fractional part, and, if present, the repeating section. If the input string represents a terminating decimal, such as 12.34, the repeating part would simply be empty. By systematically extracting these components, we set the foundation for accurately comparing the numbers regardless of how they are represented in the input. Once the input strings are parsed, the next step is to handle repeating decimals. If a number has a repeating section, we expand it to generate a sufficient number of digits for comparison. For example, 12.3456 would expand to 12.3456556, and we can define a practical limit, such as repeating the cycle 20 times, to approximate the number without infinitely expanding it. After expansion, we normalize the two numbers into a common format. This involves converting them to a decimal fraction with enough precision to ensure an accurate comparison. One of the key challenges here is handling cases where one number is a terminating decimal, like 1.5, and the other has a repeating portion, like 1.49999. By expanding the repeating section and aligning their precision, we ensure that these numbers are represented consistently for comparison. Finally, we compare the normalized values. This can be done by converting the expanded strings into floating point numbers or, more reliably, by representing the numbers as fractions. Using rational arithmetic minimizes issues with small differences caused by floating point imprecision, ensuring that our comparison is both accurate and robust. After normalizing both input numbers into a consistent format, we return the result of the comparison. If the normalized values are equal, we return true; otherwise, we return false. This approach ensures that we correctly evaluate cases such as a repeating decimal equaling a terminating decimal, for example, 0.333, being equivalent to 1/3. To guarantee accuracy, we expand the repeating section to sufficient precision during normalization. Precision is critical here, as floating point arithmetic can introduce errors. Using rational number arithmetic, such as Python's fractions fraction, eliminates these issues and ensures that even edge cases are handled correctly. Examples of such edge cases include scenarios where one number is an integer and the other is a decimal, or one number has a repeating section while the other does not. By accounting for these situations and addressing potential precision concerns, the algorithm provides a reliable solution for comparing rational numbers. To implement this algorithm, we utilize a few key data structures. Strings are used to parse and store the integer, fractional, and repeating components of the input. Fractions, such as those provided by Python's fractions fraction class, are ideal for representing and comparing the numbers as rational values with exact precision. Additionally, arrays can be used to store expanded decimal representations if manual comparison is needed. In terms of complexity, parsing the strings and expanding the repeating decimals both have a time complexity of O(n), where n is the length of the input. Similarly, fraction arithmetic is efficient and ensures precision. For space complexity, storing the parsed components and expanded decimals requires O(n) space. To illustrate, let's walk through an example. If the inputs are 0, 52, and 0.525252, we first parse them into their components. The integer part is 0 for both, the fractional part is empty for 0, 52, and 525252 for the other, and the repeating part is 52 for the first input. We then expand 0, 52 to 0.525252, and normalize both numbers as fractions. 0, 52 becomes 52/99, and 0.525252 becomes 525252/1000000. After simplifying, both values are equal to 52/99, so we return true. This example demonstrates how the algorithm handles different representations and ensures accuracy through normalization and precise comparison. This solution tackles the problem of determining whether two rational numbers, represented as strings, are mathematically equal. The numbers can include integers, terminating decimals, or repeating decimals. The solution is implemented as a method isRationalEqual within the solution class. It first defines a helper function convert that translates a rational number string into a fraction object for precise comparison. 1. The convert function works as follows. If the input string does not include a repeating part, indicated by parentheses, it directly converts the string to a fraction using Python's fraction class. If the string contains a repeating part, it splits the number into its integer, non-repeating decimal, and repeating decimal parts. For instance, 0.16 is split into an integer part 0, a non-repeating decimal part 1, and a repeating decimal part 6. It then computes the fraction for the non-repeating part by concatenating the integer and non-repeating parts. For the repeating part, the algorithm calculates the fractional value by treating the repeating sequence as a numerator and constructing a denominator based on its length. For example, 6 repeating contributes a fraction of 6/10 to the power of 1. The method then combines the fractions of the non-repeating and repeating parts to produce the complete fraction representation of the number. 2. The isRationalEqual method compares the fractions derived from the two input strings s and t using the equals operator, which ensures precise numerical equality. This approach leverages Python's fractions fraction class for exact arithmetic, avoiding floating point precision issues. It efficiently handles edge cases such as numbers with no repeating parts, numbers with empty repeating parts, and long repeating sequences. The solution is optimal for this problem, ensuring accuracy and clarity in implementation. Here, we start by defining a Java class called solution that contains the main method for determining if two rational numbers, provided as strings, are equal. The isRationalEqual method compares these two strings after converting each into a fraction object using the convert-to-fraction helper method. Within convert-to-fraction, we handle two cases, numbers without repeating decimals and numbers with repeating sections. If the input lacks a repeating section, we directly create a fraction by treating the entire number as a regular decimal. We remove the decimal point to create the numerator and calculate the denominator as a power of 10 based on the number of decimal places. For numbers with repeating sections, we first split the number into its integer part and fractional part, and then further divide the fractional part into non-repeating and repeating segments. The non-repeating segment is converted to a fraction first, which sets the stage for combining it with the repeating segment. Next, we handle the repeating part of the fractional number. The repeating segment is converted into a big integer and used to create another fraction. The denominator is calculated by taking the base determined by the non-repeating part, multiplying it by the result of subtracting 1 from 10 raised to the power of the repeating segment's length. This ensures that the repeating part is correctly scaled relative to the full fractional value. After calculating both the non-repeating and repeating fractions, we add them together to form the complete fraction representation of the number with its repeating decimal. Additionally, the helper method getDecimalPlaces assists in determining the number of decimal places in a number without a repeating section, which helps us calculate the correct denominator. Finally, we define a nested static class, fraction, which represents a simplified fraction with a numerator and denominator. The constructor of this class simplifies the fraction by dividing both the numerator and denominator by their greatest common divisor. The fraction class also includes an add method to combine two fractions. This method calculates the new numerator by cross-multiplying the numerators and denominators of both fractions and summing the results. The new denominator is the product of the two denominators. It then returns a new fraction object representing the summed value, again simplifying it in the constructor. Additionally, we override the equals method to compare two fraction objects. It checks if both the numerator and the denominator of one fraction match those of another, ensuring accurate equality checks. This is critical for comparing the two rational numbers in the main isRationalEqual method. The hashcode method is also overridden to provide a consistent hash value based on the numerator and denominator, ensuring that fraction objects can be used in hash-based collections if needed. Together, these methods enable precise handling and comparison of rational numbers, including those with repeating decimals. To solve the problem of comparing two rational numbers, we start by examining the first input, s equals 0.5, 25. The function convert is called to process this number. Since the input contains a repeating part enclosed in parentheses, the string is split into two components, integer underscore part equals 0 and decimal underscore part equals 5, 25. The decimal part is further divided into non-underscore repeating equals 5 and repeating equals 25. Next, we calculate the fractional value of the non-repeating part. Frac underscore non-underscore repeating is determined as fraction 0.5, which simplifies to fraction 1, 2. Now, for the repeating part, we note that repeating equals 25 has a length of 2. This allows us to calculate the repeating fraction as fraction 25, 10 ** 2 1 ** 10 ** 1, which evaluates to fraction 25, 990. Simplifying this yields fraction 5, 198. Finally, we combine these two parts to get the total value, fraction 1, 2 plus fraction 5, 198. By finding a common denominator, this becomes fraction 99, 198 plus fraction 5, 198, which simplifies to fraction 104, 198, or fraction 52, 99. Now, we move to the second input, t equals 0.525252. The function convert is used again, and since this input is a repeating decimal, it undergoes a similar process. The repeating sequence, 525252, is converted to the same fractional value as before, fraction 52, 99. With both inputs processed, we compare their results. Since fraction 52, 99 equals fraction 52, 99, the function confirms that the two numbers are equal and returns true. Next, let's look at another example, where we compare s equals 0, 3, and t equals 0.3333. For the input s equals 0, 3, the number is parsed into integer underscore part equals 0 and decimal underscore part equals 3. Here, the non-repeating part is empty, so non-underscore repeating equals, and the repeating part is repeating equals 3. The fractional value of the non-repeating part is straightforward, frac underscore non-underscore repeating equals fraction 0.0, which equals fraction 0, 1. For the repeating part, we note that the length of repeating equals 3 is 1. This allows us to compute the repeating fraction as fraction 3, 9, which simplifies to fraction 1, 3.
After calculating the repeating fraction, we combine it with the non-repeating part.
Since the non-repeating part is fraction 0, 1, the total value becomes fraction 0, 1, plus fraction 1, 3, which equals fraction 1, 3.
For the second input, t equals 0.3333.
We recognize that this repeating decimal is equivalent to 0, 3. Following the same process, it is converted to fraction 1, 3. When we compare the results of both inputs, we find that fraction 1, 3 equals fraction 1, 3, so the function again returns true. Now, in our final example, we compare s equals 0.16 and t equals 0.16666. For s equals 0.16, the string is split into integer underscore part equals 0 and decimal underscore part equals 1, 6. This gives non-underscore repeating equals 1 and repeating equals 6. The fractional value of the non-repeating part is frac underscore non-underscore repeating equals fraction 0.1, which simplifies to fraction 1, 10. Next, we calculate the value of the repeating part for s equals 0.16. The length of repeating equals 6 is 1, so we compute the repeating fraction as fraction 6, 90, which simplifies to fraction 1, 15. Now, we combine the non-repeating and repeating parts to get the total value, fraction 1, 10, plus fraction 1, 15. Finding a common denominator, this becomes fraction 3, 30, plus fraction 2, 30, which simplifies to fraction 5, 30, or fraction 1, 6.
For the second input, t equals 0.16666.
We observe that this repeating decimal is equivalent to 0.16.
Converting it results in the same value, fraction 1, 6.
Comparing the results of both inputs, we see that fraction 1, 6 equals fraction 1, 6, so the function once again returns true, confirming that the two numbers are equal.
To analyze the time complexity of our solution, we begin by breaking down its key steps. First, we handle splitting the input strings s and t into their integer, decimal, and repeating parts. This operation involves scanning through the strings and splitting them based on specific delimiters, such as the decimal point or parentheses.
The time complexity for this process is proportional to the lengths of the respective strings, meaning it takes m time for each string, where m represents the string's length. Since this step is performed independently for both s and t, the total cost becomes lens plus len t. Next, we focus on processing the non-repeating part of the decimal. This part is converted into a fraction object, which requires parsing the string and calculating its value. The time complexity of this conversion depends on the length of the non-repeating decimal, contributing len non-repeating to our overall time complexity. Now, we turn our attention to the repeating decimal portion, which requires more involved processing. For this part, the solution explicitly calculates the repeating fraction. The number of digits in the repeating sequence, referred to as repeating underscore len, determines the complexity of this step. Specifically, operations like calculating 10 carat repeating underscore len or 10 carat repeating underscore len 1 scale with repeating underscore len. Additionally, constructing the fraction object involves computing the greatest common divisor, GCD, which has a time complexity of log, max, numerator, denominator. In the worst-case scenario, the size of the numerator and denominator is proportional to 10 carat repeating underscore len, meaning this step also contributes repeating underscore len. After processing the repeating part, we combine the fractions representing the non-repeating and repeating portions. Adding two fraction objects involves finding the least common multiple, LCM, of their denominators and performing arithmetic operations. The complexity of this addition depends on the size of the numerator and denominator, which are determined by the lengths of the non-repeating and repeating parts. Finally, comparing the equality of the two fraction objects is a constant time operation, as it only requires checking their simplified forms. When we combine all the steps, the overall time complexity can be summarized as follows. Let n represent the total length of the longer input string, encompassing the integer, non-repeating, and repeating parts. The dominant factors in our analysis are the processing of the non-repeating and repeating parts, both of which scale linearly with the input size. Therefore, the overall time complexity of the solution is n. Shifting our focus to space complexity, we first consider the memory used for splitting the input strings into their respective components. This step requires temporary storage for the integer, non-repeating, and repeating parts, which adds up to O, lens plus len, t, space. Next, constructing the fraction objects also consumes memory. Each fraction object stores its numerator and denominator in their simplest forms, and since these values are proportional to the lengths of the non-repeating and repeating parts, this contributes O, n, space for each fraction object. In addition to the memory used for storing substrings and fractions, the solution also uses a few temporary variables during the calculations. Variables like repeating underscore value, repeating underscore fraction, and intermediate results from arithmetic operations require constant space, contributing O1 to the overall space complexity. Combining all these factors, the space complexity of the solution is dominated by the storage of intermediate substrings and fraction objects, resulting in O(n) space. To put this into perspective, we can compare this solution to a brute force approach. A naive method might involve explicitly expanding the repeating decimal up to a certain precision and then comparing the two numbers digit by digit. This approach would require OP time an OP space, where P represents the precision of the expansion. In contrast, our solution avoids this inefficiency by leveraging the fraction class. Instead of expanding the decimals, we handle them mathematically using compact fractional representations, reducing both time and space complexity to O(n). To conclude, let's analyze the best and worst case scenarios for this solution. In the best case, the input strings are short and contain no repeating parts. While this minimizes the actual processing time, the overall time complexity remains O(n) due to string processing operations. In the worst case, the input strings are long and include both non-repeating and repeating parts. Even in this scenario, the time complexity is still bounded by O(n), as the analysis of both the non-repeating and repeating parts scales linearly with the input size. This consistency across all cases highlights the efficiency of the solution, with both time and space complexity firmly established at O(n). One of the most common mistakes when solving this problem is mishandling repeating decimals. For example, a repeating decimal like 0.16 is mathematically equivalent to 0.16666, but it requires careful conversion into its fractional form to ensure correct comparisons. Another frequent issue is overlooking edge cases involving trailing zeros. Strings such as 0.200 and 0.2 may look different, but they represent the same value, so it's important to normalize them by removing unnecessary zeros. Additionally, converting strings directly to floating point numbers often leads to precision errors due to the limitations of floating point representation. For instance, 1/3 as a floating point number becomes 0.3333, which is not exact. To avoid these issues, it's better to handle numbers symbolically as fractions. Furthermore, some solutions overcomplicate the process by fully expanding repeating decimals rather than recognizing and leveraging patterns in their repeating blocks. Simplifying these comparisons by working with fractions is not only more efficient but also less error-prone. Lastly, don't forget to validate inputs properly. Malformed strings such as an empty input, a lone decimal point, or invalid formats can cause runtime errors if not handled appropriately. Now, when it comes to interviews, one key insight is that rational numbers can always be compared by converting them into fractions. For example, a repeating decimal like 0.bcd can be expressed as a fraction using algebraic techniques, which eliminates ambiguity and ensures precision. It's also important to discuss how you handle various input formats during your explanation. This includes integers like 10, non-repeating decimals such as 0.5, and repeating decimals like 0, 3. Being able to clearly articulate how your solution addresses these cases demonstrates both thoroughness and a strong understanding of the problem. Another optimization tip is to avoid expanding repeating decimals infinitely. Instead, leverage mathematical properties to directly compare the repeating sections. Additionally, clear communication is critical. Make sure to explain how you handle edge cases like trailing zeros, malformed inputs, or specific comparisons, such as determining whether 0, 3 is equivalent to 0.3333. Finally, it's helpful to draw connections to related problems like LeetCode 224 for parsing mathematical expressions, or LeetCode 43 for performing arithmetic on numeric strings. These connections can show your ability to transfer knowledge between similar challenges. To solve this problem, there are several alternative approaches you might consider. One option is fraction conversion, where both numbers are expressed as numerators and denominators. This method is highly precise and avoids errors associated with floating point arithmetic, but it requires careful handling of repeating decimals during the conversion process, which can add complexity to the implementation. Another option is decimal expansion, where you expand the numbers to a certain precision and compare their decimal representations. While this approach is simpler to implement, it's more prone to floating point errors and may struggle with edge cases, such as infinite repeating decimals. A third approach involves string pattern matching, where you directly compare the repeating blocks of the decimals to determine equivalence. This can be efficient for repeating decimals, but it often requires additional logic to handle non-repeating cases or other edge scenarios. Each of these methods has its own trade-offs, so it's important to choose the one that aligns best with the problem's constraints and your implementation strategy. That wraps up our discussion on LeetCode problem number 972, equal rational numbers. We reviewed the problem, broke down the solution, and highlighted key concepts like parsing and handling repeating decimals. Thank you for tuning in, and I hope this was insightful. Don't forget to like and subscribe for more problem explanations. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!